Chris. I don't know. My colleague, my partner is called Chris, so alla Chris. No, it means also in Latin fast and joyous, like in allegro in Italian, or alacrity in English.
Sure, like this.
Yes. Yes, and our programming language is called alacrity actually, the one we're developing. Oh yes, while we are here, I can show you the kind of things I'm doing. So let's play rock, paper, scissors, localhost. Ta-da! Ah, I need to install. Oh, this is the wrong. Rock, paper, scissors. Rock, paper, scissors. Blah blah blah. It wants me. Oh, I don't remember my password, and let me hide my password when I type it. Well, I'll retrieve it when I type it. So, where is it? This? No, this is my password. Where do I enter it? Here. Ta-da! I'm logged in. Now I can re-enable everything. Yes. So this is rock, paper, scissors, or it should be not working. Did I enter the password incorrectly? Oh, current frame. Ooh, it doesn't like. It was not interacting well with. Anyway, you can play rock. Let me play rock against anyone. I'll play against myself. That would be simpler. So I'm going to sign a transaction for rock. Ta-da! Ooh, 1 million gas. That's a lot. That's not good, but anyway. And then I'm going to play. No paper. I'm going to play in that game. Or I'm going to wait for this thing to be confirmed. Ta-da! So I'm playing rock, paper, scissors on the blockchain. This is very stupid. And what is interesting about this rock, paper, scissors is that the source code is supposed to look like this. This is one version of the source code. It's a bit. This is one version of the source code in like 50 lines of code. And what we produce is, and it's not the shortest version of the source code. What we produce looks like that. So a contract which is 300 lines, equivalent to 300 lines of manual code, and in Solidity, and a client which is also the backend, which is also 400 lines of code that would have to write manually, and the two would have to match exactly, and all in all, it's like 2,000 lines of JavaScript, and you get any of this thing wrong, you lose all your money, of course. Or there are any bug in there are scenarios where you lose your money. So we want to take this abstract program, and this is not the most abstract version. Where was it? Something like that. We take something like that and we produce a program where. So what is interesting in this program is that there are parts that are done in the consensus and parts that are done in one participant. Oops. These declares are two participants, and one starts with some parameters, and participant A does some computation. And tells the result of these computations to participant A does some computation, and at some point it tells this computation to the consensus. Now the information is public, and then at some point participant B does some other computation, and B tells everyone about the result of this computation. And then, so we have a computation where there's a consensus, what everyone agrees on. And this part is public and owned by all participants. And there are parts that are private to the participant. And that makes the language interesting. If you have seen connection machine Lisp, they had a notion of zapping, was data structures where some of the data structures are the same replicated on all of the nodes. and you can escape from this common computation to be, oh, on this node this happened, on that node that happened, and it will be specific to the node. So you can describe a computation that has part that is common and part that is specific. And when we develop a multi-party computation, that's what we're doing. We have a computation where some of the thing, notably the outcome of what money goes where, will be common knowledge. I mean, the thing that everyone agrees about. Like, you've got these tokens, now you won, so you got mine too, or the other way around. And the other part that remain private, you don't want to show your hand too early, or the other guy will play the hand that wins against you. So you have computations with a consensual part and private parts. So that's the kind of things we're doing.
How do you keep it private for the proof on the
I'm not sure what you mean. In practice, it's run on your computer and you don't publish the result. That's how it works. And your hand remains private on your computer until you reveal it, and his hand is private on his computer until he reveals it. So when you choose your hand, you don't see his, and when he chooses his hand, he doesn't see yours. And to do an exchange, for instance, the first of you who will publish something, who will not publish his hand, he will publish a salted commitment so that his hand is chosen. Your commit you're publishing as a digest, you can't choose your mind afterwards, but the other one cannot see it. And then the second one, so in this thing, it's done somewhere, his commitment is a digest of his salted hand, and his salted hand is a concatenation of some salt and his input hand.
Okay, that makes sense.
So the first person chooses a hand but does not show it, instead she shows a commitment. The second person, since he's the last person, can directly show his hand here. And so that's how you can write programs where parts happen on your computer and parts happen on the consensus. Okay, so let's go after this demo, stupid demo. Let's go on the. Actually, I didn't finish the demo, did I? Maybe I should reload here. No contractive game. Well, there's a bug somewhere. I don't care to debug things right now. Let's go to this actual talk. Why writing blockchain application is hard and how functional programming can help, also known as language abstraction for verifiable blockchain decentralized applications, which is my kind of Lambda talk. Okay, so first start with challenges for secure distributed applications or decentralized applications. Why do we have no good decentralized applications today? It's a vicious circle. There are no applications, therefore there are no users. There are no users, therefore there's no money in it. There's no money in it, therefore there's no money to develop the technology. There's no money to develop the technology, therefore there is no good applications. And another way of calling a vicious circle among technologists is a bootstrapping issue. So, hey, it's easy. We just have to break the cycle by bootstrapping somewhere. And since we're technologists, well, of course, the somewhere is a technology that we are going to address. So what is the missing technology? People say, oh, blockchain missing scalability because the common blockchains have like 10 transactions per second. Or interoperability, where you want to write a program while it runs just on this blockchain and cannot interact with other blockchains. Portability, it runs on this blockchain and the code is totally different if you want to run on a different blockchain. Usability, it's totally horrible to use. You've seen me try to use a simple blockchain application. It was very hard and it failed. We can do better. But the main problem is security. With blockchain, it's very hard to have security. And why? Because the transactions are high stake, which means that if you have a bug, you lose all your money. And it's irreversible. So you lose all your money and there's no way to get it back. There's no recourse. Which means that your bug budget is zero. One bug, you lose everything. Someone's going to be pissed and go at you. That's bad.
How do you be negative?
And zero is a hard zero. And code is fragile. And code is always fragile in all languages. And all existing languages, tools, and methodologies yield fragile code because they don't even try. In most programs that you write, it's okay to have bugs. If you piss off 1% of your customers, that's nothing. You can fix the bug and issue a new version, and the new customers will be happy, etc. That's fine. But on blockchain, you find the bug, you fix it. Well, maybe your program does not have this bug, but the customers who use the program still lost all his money and is still very pissed at you. or you lost your own money and well, sorry. So code is fragile because most people don't even try. Who tries? Maybe NASA or the aerospace industry tries to have code that has no bugs. The hardware industry, Intel, people who have processors try to have code that has no bug because if there's a bug, they need to do a recall. It's very expensive, and the manufacturing cycle is like 6 months to a year or more. So these people want to have no bugs, but these people don't fight what we fight in the blockchain. In the blockchain, we fight a hostile internet, where if something can possibly go wrong, such as, by once in a blue moon, if an electric surge happened at the wrong time, well, you lose your money. Well, if you have something like that for NASA or Intel, well, NASA, okay, once in a blue moon, you just don't launch your rocket. Once in a blue moon, just launch it a normal day where there's no weather incident. If you're Intel, okay, we have to have an errata to don't use this instruction in our processors. But with a blockchain, no, if you have a bug, the bad guys will deliberately make the bug happen. They will wait for the blue moon, they will make the power surge at the wrong time, and they will take your money. So you have zero bugs, and you're not fighting natural accidents. You're fighting dedicated attackers who want all your money. And every cent that you have in your day app is an incentive for the bad guys to break your system. So unless your business plan is to have no success and no one using your dApp with any real money, if you plan for success, you must plan for zero bugs. Yes? Okay. So that's why programming for the blockchain is not just hard. It's the hardest thing there is. It's even harder than writing software for NASA or software for your hardware for your processor. And of course, the solution here is logic. You are all in functional programming language people. Okay, you will think, sure, when someone writes a program for the blockchain, they may issue automation and logic and mathematics, but the bad guys won't. So if there's any technique whatsoever in logic that can find the bugs, and if you don't use it yourself before the program is out, the bad guys will use it after the program is out, and they will take all your money. So we have to use Dijkstra's approach and prove all the code correct with mathematics before we deploy it. And of course, Dijkstra said this is true of all software. I don't believe this is true of all software, but I believe this is true of all blockchain software. So Dijkstra was right, just not about the correct thing. Of course, when you want to prove software correct, the easiest way to prove a piece of software correct is to scratch it and rewrite it from scratch with proof in mind. So you can't retrofit mathematics into your code. You have to add it from the beginning, and that's why it's hard. And that's why logic must be part of your development methodology. And finally, complexity makes math intractable. If you have a very simple problem, you can search for all the possible solutions. The space will be small, you'll find a solution, no problem. You push the button, it finds the answer. If your problem gets a bit bigger, then the search space becomes exponentially larger, and soon you have no chance to find the solution through automatic dump means. So complexity quickly makes math intractable. So the number of possibilities and interaction you have to deal with is impossible. That's why to prove software correct, you have to adopt radical simplicity, which doesn't mean that you take a simpleton and have him write the code. It means that you take someone who understands what is simple in mathematical terms and write the code. And what is simple in mathematical terms is very different from what is simple in psychological terms. And that's a big problem. It means that you need people who understand math to write the code, and that doesn't scale. So how can you write software as a blockchain and make it available to normal people? You need something more. And everything I said so far is pretty much common knowledge, consensual. Everyone agrees on it or should agree on it. What I'm going to tell you now is what Alacruz is doing that we believe is somewhat different from what other people do and believe. We believe that, yes, building software for the blockchain is extremely hard, but if we use a domain-specific language, we can make it tractable. We believe that we can automatically achieve the prove the correctness of a program by cascading the proof from the high level down to the low level, which means you take a very high level specification. This is a poker game, this is a rock, paper, scissors, this is a derivative contract, this is a non-custodial exchange, whatever it is you're trying to build as an application. You take a very abstract view that will be only a few tens or hundreds of lines. You will compile it to some level lower, and some level lower, some level lower. And at every level, you will produce a proof that it's correct. And at every level, and this is how you can prove the whole thing correct. If you want to write 1 million lines of code and prove it correct, this will not work. But if you use the DSL approach at every layer, this will work. And third, our third thesis is that we have a blockchain agnostic model that we call consensus as court. And they presented last year at LambdaConf. And that will solve all the usual technological problems through logic. OK, so what is our domain-specific language? And first, why don't we just have a library? Well, the reason we want a DSL and not a library is that a library can help you do everything, but it cannot help you prevent anything. Or, OK, with a type system, it can prevent you from violating the type system, but even the type system of, say, Haskell will let you do a lot of bad things, which means that you have a lot of global invariants in how you use a library that are not enforced by the type system or your language, that you have to enforce by hand, or else there's a bug and you lose all your money. Which means that the library solves the problem, but it introduces another problem, which is using the library properly, using invariants that are not enforced by the language. So you buy something, but you still lose something. And if you just use one library, that's fine. You have leaked some verification, some complexity, but you have made verification harder. And with one library, that's fine, but it will get worse with multiple libraries. With a domain-specific language, you can express both the positive thing that you want to say and the negative thing that you have to do, the constraints. And these constraints are not limited by your language, host language's type system. They can be whatever makes sense for your domain. And it's not because it's not enforced by the type checker necessarily, but it's enforced by whatever code your DSL processor does. So you're not limited by the type system. You can really enforce the things that matter for your application. And that's why you can seal the complexity away. You can make it so that we solve the problem for you, and you don't have this additional problem of using the thing properly. We can do that for you. And that makes verification easier rather than harder. And if you ask why don't we use a general purpose language that is better, the answer is that a general purpose language that is better would be just a way to have lots of libraries and combine them. And then every library would leak a bit of its complexity. And soon, this complexity will multiply and multiply, and exponentially, you'll have a problem that is soon intractable. And the way I see it is that your problem really has multiple levels of abstraction. And if you try to replace that by a library, that means you're trying to mush all these layers of abstraction into one layer of abstraction. Oh, this is the Haskell program, or the C++ program, or whatever it is. And you try to mush the layer of abstraction together, but the complexity builds up on the side. All these interactions between all these levels that you have not isolated from each other comes and bites you. And that's why a general purpose language is not the solution. What you need is a DSL that can keep the problem space small by saying, this problem space is small, this problem space is small, this problem space is small, and none of them leak. And therefore, the proof I have to produce is a linear in the size of this tower rather than exponential in the size of a tower. And with a DSL approach, you're general purpose, but at the meta layer, at the meta language. Your program itself is very domain specific, and that's fine. It does one thing, it's specific to its own domain. But the general purpose logic is at the meta level. OK, why don't we just use a contract language, such as like better Solidity or whatever people come up with these days? I will argue that the distributed application is much more than a smart contract. It has code running on your clients. It has code running on your servers or validators, whatever you have. And if there's any bug in any of these components, your money is gone. You have a perfect contract, but your server or your client is incorrect, well, your money is gone. You have the perfect contract and the perfect client and the perfect server, but they were compiled with slightly different options, poof, your money is gone. So any discrepancy is a bug and everyone's money is gone. The only way to make sure that all the components are correct and are in sync and combine well with each other is to have a single spec somewhere. And this single spec specifies the entire application, and from this single spec use a technology called endpoint projection, which means that I will extract the smart contract, will extract the code for the server, for the client, for whatever actors there are, and I will do it correctly and consistently across components. If you're trying to do any other way, good luck. So can we share a virtual machine with contract? Some people say, oh, we should have this contract virtual machine for that. And the answer is no, still emphatically no. A contract virtual machine is for deterministic consensual computations, which means that everyone will, on the blockchain, every validator will replay the same program and verify that it has the same answer. Millions of people will replay the same program. That's why it's literally 1,000,000 times more expensive to run code on the Ethereum VM than to run it on Amazon. And so the cost is so high that when you write a contract, a VM, what you want is to optimize your programs for cost. And so the VM must be optimized to deal with this cost issue. When you write a decentralized application or distributed application, what you're really writing is an asynchronous multi-party computation. You have several people who want to deal with each other but don't trust each other completely. So they use this blockchain as a judge, but most of what they do is they do directly to each other. They are going to play poker, they are going to play online games, they are going to exchange foreign currencies for crypto coins. I don't know what they are going to do, but they are going to do with each other as fast as they can, and most of it will not run on the blockchain because it's too expensive. Most of it will run on their private cloud, their private computers, and what you want to optimize for is auditability. Why would you put any money in an application that you don't trust? And how can you trust an application if it's millions of lines of code? What you want is optimize for the fact that, oh, actually, it's not 1,000,000 lines of code. Actually, this is rock, paper, scissors, it's 20 lines of code. So I can trust it. I can myself read the code and trust it. Or I can have Jimmy or someone I trust read the code and say, yeah, hey, you understand this kind of thing. Can you tell me that it's right? And it says yes. And he can say yes because it's only 20 lines of code. If it were 1,000,000 lines of code, he'd say, no, you'd have to pay me for 10 years before I audit it, and by the time it will be totally useless. So what you want to optimize for is not at all the same thing for a VM, contract VM, and DApp VM. So what do I want in my DApp DSL then? I want functional programming, of course. That's the core of any programming that you can reason about, where logic and programs are the same. You want functional programming at the core. You want asynchronous and synchronous communication. Asynchronous because we are multiple actors talking to each other. Synchronous because that's what the blockchain provides. It provides a synchronous way to exchange data where you know that the data is there. You want cryptographic primitives. You want modal logic and in its epistemic and temporal variance, so that you can reason, oh, I'm going to send a message, A sends a message to B, therefore now B knows that thing, but he knows it within that time frame, and you want to be able to prove that secrets don't leak. You want to be able to prove that the protocol will finish in finite amount of time, things like that. Linear logic, you want to reason about the resource and resource management. Game theory, you want to reason about economic equilibrium. Are the actors interested in playing, or is an actor systematically interested in cheating? Then the protocol is worthless because no one will ever play this game. You want refinement logic, which is what allows you to reason out multiple levels of abstractions. And optionally, you want finitary logic, which is what allows you to use finite circuits and zero knowledge proofs. So these are the things I want in a DApp DSL. And of course, if you want to write a program that has all that in it, you will fail because it's way too complex. What you want is an extensible framework to add those things. That's why right now we're using Racket, but whatever you use, you need a framework that allows you to add all this complexity in a way that's manageable. Okay, so how do we do cascading verification? We have a semantic tower. So you must think of your programs in like your DSL implemented in Haskell, implemented in some Haskell core, implemented in whatever, implemented in LLVM, implemented in user level x86, implemented in actual x86, implemented in silicon, implemented in quantum mechanics, whatever it is. So you have this tower of semantics. And it's mind-bogglingly complex. But if you can separate it in layers that are small and tight, you can reason about it. And you want to reason about it from the user specification down to, say, the bit bashing. Let's say for now we trust the hardware. So we'll want to prove the software correct from the 20-line software, 20-line rock, paper, scissors program you write or derivative contract you write, down to the program that takes bits and encodes them and sends them over the network. And every issue will have to be addressed at the proper level of abstraction. So first thing you want, in this tower of abstraction, that there are no semantic leak. A semantic leak is something that means that some low-level series of interaction cause a high-level interaction that was not allowed. So I can cheat the system. I can make the system do something it should not be allowed to do. That's what a semantic leak is. So the first thing you want, the property that programming language compiler series called full abstraction, no semantic leak. And then you want to be able to address each issue at proper level of abstraction, which means you want to be able to zoom in and out of this tower. You want to go up and down in the layer of abstraction. And you want to do it at compile time. That's how you reason and compile the program at all. But you may also want to do it at runtime, which is how you address runtime problems. If the problem is that a message didn't go through, you must identify that a message didn't go through, and you must go back up the stack. This is a message that this $1 million contract depends on, so you better make it go through. Or this is a message that will cost you 3 cents. Forget it, let's drop it and lose those 3 cents. So you must be able to trace what the problem is, where the important problem is, and address it. So that's why you must be also able to zoom in and out at runtime. And importantly, regular developers should not have to write the proofs. You don't want regular developers to learn coq and dependent types. It will never work, it will never scale. You want them to automatically get the proof they need using Z3 or an automated story improver. On the other hand, people who extend the system, yes, you can and should require them to learn dependent types and prove the correctness of our system. Or say, hey, you improve it, trust me if you want, but if you just, someone has to prove the correctness of the system if you want to be serious. Okay, so what do we want to automatically verify? There are, of course, user-defined protocol invariants. You are playing rock, paper, scissors. What does it even mean to play rock, paper, scissors? I cannot decide that for you. You have to decide that, and you have to specify that. And we can help you to some point, but we cannot do the work for you. If it's a derivative contract, what is a derivative contract? You have to convince everyone else who wants to participate in the contract that your contract does what it's supposed to do. That's your invariant, that's on you. We can help you with, for instance, dealing with linear resources, the fact that the money will not be dropped on the ground or created out of nothing. We can help you with that. Access control, the fact that only the people with the correct keys will access the right thing, we can help you with that. Time bound, the fact that the protocol terminates, we can help you with that. What we can help you with that is very important and specific to blockchain is game theoretic liveness and safety. Game theoretic liveness means the protocol will make progress and terminate if all actors are honest. If all the participants want to play this poker game, the poker game will indeed happen and complete. And that we can prove automatically with our system liveness. Safety is very important. It means for each of you, if the other actors conspire against him, he will still not lose his capital. If this gentleman here is playing poker and you two are playing poker against him and you're cheating, you're using lots of things not in the protocol, not in the book, all the tricks you can to make him lose his money, you can't. All you can do is make him waste his time until he say, okay, I'm out of here, and I take back my money. You cannot cheat at poker, you cannot steal him. Even if you don't follow the protocol, all you can do is cheat yourself and waste people's time and a bit of gas to partake in the system. So safety is very, very important. It can also be proven automatically, but it's an essential property of blockchain applications that no one else is even thinking about. So what verification techniques do we use? Type theory, you are all here familiar with coq or things like that. Theorem proving, it's automatic proving with things like Z3. Model checking, well, we can extract domain-specific models of what's going on and prove them automatically. Strength spaces is a very important thing, is how you model attackers who do not follow the protocol. Most programs focus on what happens if the protocol is followed and et cetera happens. But what about if the protocol is not followed? The whole point of an attacker is he will not follow the protocol. Well, you need to prove that even if some attacker does not follow the protocol, he can still not do the bad things that you should not be able to do. Dynamical system simulation, just because you've proven it correct doesn't mean it's correct. You have to actually test the code and test the model of the code or whatever to make sure that you haven't forgotten anything. And composable implementation layers. That's how you keep complexity in check. That was also the subject of a previous talk of mine at LambdaConf. First-class implementation basically use category theory to model a computation as a category where the nodes, the states, the objects, or the states of your computation, the arrows between those states, the morphisms between those objects, or the label transitions. And so this defines one computation. And then implementation is a partial functor between two of these computations. And you can have game theoretic safety and liveness as composable properties of these implementations. So you can prove it at each level, and it composes it as a proof of liveness and safety of the whole thing. And you can have lots of other features, you might talk. But the important thing is that functoriality is the same as full abstraction. I told you that the one essential property you want in these towers of semantics is that there is full abstraction, which is a property that allows you to reason at one level at a time. Well, functoriality is exactly that. So when I say that an implementation is a partial functor, that is exactly what allows you to reason at one layer at a time. If you don't have this property, you lose. And if you have it, you have category theory naturally. Just because we believe in formal methods doesn't mean we don't believe in less formal methods. The two are complementary to each other, not replacement for each other. For instance, there are lightweight formal methods. You don't prove that there is no bug, but you can prove that there is no simple bug. And the bad guys will use those tools. Either a simple low-hanging fruit to take the money. And they will use these tools, so you should use these tools, otherwise you lose your money. So you want to starve the attackers of low-hanging fruits. With formal methods, you also need axioms. I'm making all these assumptions about my program. And most people, even who use formal methods, they make assumptions, and then they forget which assumptions they make. Then they change the program. Then some of the assumptions are invalidated, and then you have the Ariane 5 explosion, where you assume the program has the same assumption, but actually it doesn't. And then you have floating point exception, and $1 billion of a rocket ship explodes. So with formal methods, we can't do without axioms, but we can track the axioms, and so users can audit them later. So you have to audit them, but at least we can track which axioms you depend on, and that's very important. But still, you need to audit them, which means that in the end, the human processes matter. Someone needs to audit all the things all the time, and certainly before deployment, you need to have good design, good review, good discipline. You need to have checklists. You need to have a red team. You need plenty of human things that no amount of formal methods can ever replace. So the two, once again, are complementary. And conversely, no amount of manual checking can replace the assurances that formal methods will give you. So now let's talk about a blockchain agnostic model of consensus as court. Who here has seen my previous talk of last year? No one? Okay. Yes, Jimmy. Thank you, Jimmy. So here are the cliff notes. It's an analogy between the blockchain consensus and a human court system. An analogy for a functional programmer means that there's a higher common abstraction, and you instantiate it with different parameters. So what you end up with is different things, but the important thing that is common is actually the higher abstraction. And this higher abstraction is systems for avoiding and resolving conflicts. And the different parameters have to do with using humans versus machines. So avoidance and conflict, what does it mean, for instance, to avoid conflict? When we play our poker game, we'll play it without sleeves, and we'll play it on the table with a deck of cards provided by a trusted judge, and the trusted judge will remain here to watch us. So that's how we avoid conflicts, and happily it's very expensive because we have to hire this trusted third party and meet in person without sleeves, so it's a toll, but at least it's a reliable thing. It's expensive, but it's reliable. Conflict resolution is when we're going to play the game and we're taking maybe to tape it or something. And at the end of the game, if everything goes right, that's fine. We never had to hire a judge or anything. But if the thing goes wrong, then we have to go to the judge and we have to argue the case. We have to show the taping. We have to, it becomes slower and more expensive. But the happy case will be faster and cheaper. So with humans, verification, consensus, the court system is where people use legal arguments with rhetoric. And the great thing about legal arguments with rhetoric is that it can adapt in case you forgot an assertion at the beginning. It's flexible. It's slow. It can take years to resolve a case in court. It's expensive. It takes millions of dollars in lawyer fees to resolve a case in court. But it's quite flexible. It can do lots of things. With machines, it's totally different. You have verification games that use logic, which is fast, comparatively to humans. Like a slow system will resolve a case in a week or something. It's cheap. It costs cents instead of millions of dollars to run the system, but it's rigid. If your contract or whatever you do did not have all the cases figured out in the beginning, someone is going to have a bad time. So very different. There's an analogy, but the two things are very different. And what does that mean in terms of smart contracts, which are either smart or contracts? It means that now you can use any arbitrary logical formula as part of your smart contract, which of course requires your logic model, a logic model of any blockchain or sidechain that you're going to use in your smart contract. But when you have a logic model of whatever computation you're doing, you can write the specification as logical formula of what it's supposed to be done, and then you can use game semantics to translate these formulas into verification games. And the fundamental theorem of game semantics says the good guy has a winning strategy. And since the good guy has a winning strategy, it means the bad guy will always lose, and then he will pay damages and court fees out of a bond that's deposited as collateral, which means that now everyone is always interested in not cheating because they know that if they cheat, they will be caught and they will lose their collateral, which means that no one ever cheats, which means that no one ever executes the code in the contract, and that's great. You write code that is perfect so that no one ever runs it. There is a small catch. It's not enough that there exists a winning strategy. You must know the winning strategy. And you must know it without having to break the cryptography, which would defeat the purpose of the system. Which means that if the contract is about a series of transactions that the other guy does, you must be able to see what these transactions are. And in a simple case, you have state channels where everyone needs to sign every state before it becomes valid. So of course, nothing will be valid unless you see it and unless you approve it. But if you want to have an operator that goes very fast, you need different systems. So there are things like plasma, sidechain, etc. And in the end, you need what we call a data availability engine, a way to make sure that the software, that all the data that you need to discuss will be made available. Which means that we can scale any application on a sidechain using a general purpose mutual knowledge validator network. The term common knowledge is what everyone knows that everyone knows that everyone knows that everyone knows. That's what the consensus brings. Mutual knowledge is just what everyone knows, and it's much simpler. You don't need consensus for that. You can parallelize it infinitely. It's very easy to shard. You can get it in just one round trip around the world instead of lots and lots of round trips around the world. So mutual knowledge is much cheaper to achieve than consensus, which is why we can scale things for cheaper with a mutual knowledge network than we can with a blockchain consensus. And so there. So by looking at the logic of what is a blockchain, we can achieve a general purpose scaling solution. Zero knowledge proofs. Well, that's an extension we don't need to worry too much about, but if you can think in terms of finitary logic, you can achieve privacy or non-interactive. You can achieve a lot of things with zero knowledge proof. But the important thing is, if you can have this system that is blockchain agnostic, now you can have one application which is very abstract. This is rock, paper, scissors, this is poker game, this is a derivative contract, this is whatever it is. Something expressed in the high level of the assets you're manipulating and the rules for how they are being transferred. And you can then compile it to one blockchain or the other, like Tezos or Ethereum or Cardano, whatever you want. You can have interactive verification through this game proofs or something non-interactive using zero-knowledge proofs. You can have public or private computations. You can have a slow and trustless thing where you sit on the table and do everything in the contract, or you can have it fast with a semi-trusted middleman. There are plenty of different options for how you compile your application in the same application. The only thing you have to audit is one, the application, two, each of the compiler toolchains. So in a linear time, you can prove exponential number of combinations of applications. And of course, when you do a $10 poker game, you are not going to use the same implementation for a $1 million poker game. So different people using different blockchain with different amounts and different needs will use different compilation flags for their applications, and that's fine. And you only need a linear amount of work to prove all these combinations correct. Try to do that with any existing framework, you will not be able to do that. So what we did with this blockchain agnostic model, we can solve all the usual problems that blockchains have, and we can solve them because we have gone back to the mathematical essence of a blockchain, which is common knowledge about monotonic verifiable data structures. Data structures, you know that, you're programmers, functional programmers, you build data structures. Verifiable, you Merkleize them, so you make them content addressed by the digest of the content. Monotonic means that you can only add information, you cannot contradict past information. And common knowledge is everyone agrees on the thing. So when you put that in those terms, the logic, the mathematical logic that you need for that becomes apparent to anyone who's trained in those domains of mathematics. And then you can solve all the above problems and more by going back to the mathematics of it. Conclusion, our take-home points are that, one, building secure distributed applications is extremely hard, but we can make it tractable with a domain-specific language. Two, we can prove the software correct by cascading the verification from top to bottom, from the user specification down to the bit banging, using full abstraction, which is very important. And three, with our blockchain agnostic model of consensus as code, we can solve all the usual technical problems of blockchains through logic. And in the backstory, if you step back, the meta story is that to solve any difficult problem, you have to go back to the mathematical essence of things. And that's what we call category theory, like going back to the mathematical essence of things. And the way that works is that you are going to strip the problem of all the incidental complexity, all the complexity that does not have to be there, all the make work that people do because they don't think about the fact that it's not essential. You go to the essence of the problem, you strip all the incidental complexity, you focus on the essential complexity of the problem. You identify what is the thing that deserves to be there and the thing that doesn't deserve to be there. And in the case of blockchain, you must embrace the fact that there are lots of levels of abstraction. If you don't embrace this fact, you will end up with extraordinarily exponentially complex thing. You need to cut your problem into small layers that you can compose. And for that, you have to reconcile semantics and reflection. Semantics is reasoning about what the program does in a way that it cannot change at runtime in any way. And reflection is all the ways the program can change at runtime or compile time and do all the things you need to do. And the problem is, in this world, the computer scientists who do semantics do not consider reflection, we don't want to touch it. The computer scientists who do reflection do not want to think about semantics. Well, the two will have to talk to each other to solve this problem of blockchain and all the other associated problems. So, thank you for listening. I am Rene Rideau from Alacris. If you want to know more, we have a website and a Medium account with lots of articles. We have a Telegram channel, and we also have a code repository of repositories on GitHub. Thank you for listening, and now if you have any questions, maybe we have time for a few of them. Jimmy?
So with your extensibility, having a tower of
yes.
individually verified layers,
yes.
it defeats the exponential explosion of
yes.
end-to-end verification.
Yes.
Because you're restricting global interaction between the layers?
Yes. Every layer has to be isolated from the other layers, and that's what full abstraction is about.
Okay. And then how do you, so that it's going to be linear in your number of layers?
Yes. Then the proof is linear in the number of layers.
Intra-layer, you could still have...
Inside a layer, you can have bugs, and then you have to prove that there are no bugs inside the layer, and it's...
So then does the DSO...
So
does it only provide the hygiene between layers, or does it also provide a proving intra-layer?
Yes and yes. So what it means is that within a layer, you have to prove that the layer does the right thing, and then indeed the translation proves that each layer of translation is correct. And a lot of this work can be done once and statically. For instance, when we provide our entire tool chain, we'll provide the proof with the toolchain that this step of translation is correct. And then at the top, we'll provide you a tool to specify what you want your small program to do. And you will have to provide the proof of that. But at least the translation, all the translation will be correct. So if you start from a correct program and you use our correct compilers, you will have a correct thing at the end. Correct modulo axiom that you want to check. One of the axiom would say, hey, you will be able to send this message within a day. Whether you have 3 redundant data centers or whether you will take the plane to the other country that doesn't have an internet outage, whichever way you do it, one of the assumptions is the message has to go through within a day or whatever the timeout is. So there will be a set of axioms and your Intel computer works the way it promises to do, etc. I mean, there are still axioms that you need to check and to enforce, and we can do that for you, but we can prove the correctness within those axioms. No.
I'm curious. So, what do you have generating from the DSL that you have right now? Is it just JavaScript, or do you also?
So right now we generate both Solidity and JavaScript from our DSL.
So you already have Solidity generation.
Already have. Our compiler is not as complete and bug-free as we would like it to be, so I wouldn't say that we already have it, but our plan is to release by next week a first version that indeed compiles correctly, without a proof of correctness, but correctly the rock, paper, scissors.
That's excellent. Are you planning on just compiling to Solidity, or can you eventually do compiling to bytecode?
Yes and yes. I think eventually we want the EVM bytecode. And eventually Bitcoin, whatever scripts and everything. But we start with what is easy so we can demonstrate it. But yes, eventually, I don't think we'll ever have a proof of correctness with Solidity. It would be way too complex and pointless. When we start actually before we start doing proof of correctness, we'll do EVM directly. Okay. And there are already frameworks that do that, so that's fine. Last question or no last question? Okay, last question.
Is there any potential way that you could extend this to have a backend for snarks?
That's the plan. That's on the roadmap. Yes. When I said like we wanted to do, yes, this is totally on the roadmap. Here, yes, we want to do backend for snarks. Yes. Thank you, and thank you for coming, and thank you for listening to this talk.